there is a satellite called Vanguard 1 that has been orbiting Earth since March 1958. It weighs 1.47 kilograms. It is roughly the size of a grapefruit. It stopped transmitting in 1964. And it has been silently circling the planet at an altitude of between 3,760 and 4,900 kilometers for more than 60 years, with no power, no function, no purpose except to continue existing in exactly the orbit that the physics of 1958 put it in. It is the oldest human-made object currently in space. It was not designed to stay up there this long. Nothing that put it there thought about what would happen after it died. It was simply launched, and it did its job, and then it stopped, and then the world moved on, and Vanguard 1 did not. We do not know exactly when Vanguard 1 will fall back to Earth. The model suggests somewhere between 2,100 and 2,300 years from now, depending on how solar activity evolves over that time. By 2200, the people living beneath it, if there are any, will have no memory of who built it, what it was for, or who to notify when it finally burns up in the atmosphere. There are currently more than 25,000 objects in orbit around Earth that the United States Space Surveillance Network tracks. Of those, roughly 11,000 are active satellites doing useful work. The rest are dead satellites, spent rocket stages, mission-related debris, and the fragments of objects that have broken apart or collided in orbit. There are an estimated additional 500,000 objects between 1 and 10 centimeters in diameter that are too small to track reliably, but large enough to cause catastrophic damage to any operating satellite they strike. There are millions more smaller than 1 centimeter. Every one of those objects got there because someone sent it there, and essentially none of them were sent with a fully adequate plan for what happens when they stop working. Tonight we're going to follow a satellite from the moment it fails, not from launch, from death. We're going to look at how satellites actually die, what kills them, and what the physics of orbital mechanics does with a dead machine in the years and decades and centuries that follow. We're going to look at the specific orbital shells around Earth and why some of them are approaching a point of no return. We're going to look at the cascading collision dynamics that one researcher predicted in 1978 and that we are now watching begin to materialize. We're going to look at the human attempts to solve this problem and why those attempts are, so far, running far behind the rate at which the problem is growing. And we are going to look at the political and legal landscape that allows the most crowded highways in human history to operate without any enforceable traffic management. If this is the kind of mission briefing you want more of, subscribe and stay with the crew. Strap in. We begin. The specific number, 25,000 tracked objects, deserves more unpacking because the way space surveillance works reveals something important about the nature of the debris problem. The United States Space Surveillance Network is the primary global system for tracking objects in Earth orbit. It consists of ground-based radars and optical telescopes operated by the US Department of Defense and distributed around the world. These sensors continuously scan the sky, detecting echoes from radar pulses and recording the positions of bright objects against the star field. The data feeds into a catalogue maintained by the 18th Space Control Squadron at Vandenberg Space Force Base in California. The tracking threshold, the minimum size of object that the surveillance network can reliably detect and catalogue, is approximately 10 centimeters in low Earth orbit and approximately 1 meter at geostationary orbit distances. Objects smaller than the threshold are detected occasionally but cannot be reliably tracked. This means that the 25,000 tracked objects are only the visible tip of a much larger population. Below the tracking threshold live hundreds of thousands of objects that are real, physical, moving at orbital velocities, and fully capable of destroying a satellite on impact. A 10-centimeter fragment of aluminum moving at 8 kilometers per second, relative to a satellite it strikes, carries roughly as much kinetic energy as a car at highway speed. The impact is not damaging, it is catastrophic. Even a 1-centimeter fragment carries the kinetic energy of a rifle bullet and can penetrate and destroy critical satellite subsystems. The gap between the tracked population and the real population is the central operational challenge of space debris. Satellite operators can maneuver to avoid objects they know about. They cannot maneuver to avoid objects they do not know about. Every operational satellite passes through clouds of untracked debris on every orbit, with collision probabilities that are low per orbit but non-zero, accumulating over years of operational life into a risk that is far from negligible. The catalogue has a specific entry for a grey thermal glove lost by astronaut Ed White, during America's first spacewalk in 1965. The glove no longer exists as a tracked object. It re-entered the atmosphere long ago. But its brief membership in the catalogue represents something true about the nature of the debris environment. It is everything that humans have ever let go of in orbit, still there, still moving, organised by orbital mechanics into a layered environment of extraordinary complexity. But to understand the full scope of what happens to satellites after they stop working, you first need to understand the scale of what we have put up there and why it accumulates the way it does. The orbital inventory of Earth is not what most people picture when they think about satellites. The popular image is a clean, orderly sphere with communication satellites evenly distributed in geostationary orbit, GPS satellites in their precise constellation patterns, and the International Space Station tracing a visible arc against the night sky. The image is not wrong exactly. Those things are there, but they exist inside a context that the popular image leaves out entirely. The context is everything else. The space age began in October 1957, when the Soviet Union launched Sputnik 1. That satellite was a polished metal sphere 58 centimeters across, beeping steadily on radio frequencies that amateur radio operators around the world could detect. It lasted 21 days on internal batteries before going silent, and it decayed from orbit and burned up in the atmosphere in January 1958. Sputnik 1 came and went cleanly, but not everything that followed did. The second satellite ever launched was Sputnik 2, which carried a dog named Laika in November 1957. Laika died within hours of launch from overheating. Sputnik 2 did not have a re-entry capability. It burned up in April 1958. These early objects mostly gone. But the objects that followed occupied higher orbits, and the objects that occupied higher orbits did not come down. By the early 1960s, the practice of putting satellites into high orbits, beyond the drag of the upper atmosphere, had made the permanence of the debris problem concrete. Early communication satellites were placed in geostationary orbit, 35,786 kilometers above the equator. Objects at that altitude experience essentially no atmospheric drag. They will remain in orbit until something perturbs them, and nothing in the current environment is likely to perturb them significantly. The first objects placed in geostationary orbit in the 1960s are still there, every one of them, dead but present. Today, Earth is surrounded by objects in a shell of space from roughly 200 kilometers altitude to tens of thousands of kilometers altitude. Not a uniform shell, a structured layered environment in which different orbital altitudes host different populations of objects with different properties and different fates. The lowest layer, what engineers call low Earth orbit or LEO, extends from roughly 200 kilometers to 2,000 kilometers altitude. This is where most operational satellites currently live, including the International Space Station at about 400 kilometers, the dense constellations of Starlink satellites at about 550 kilometers, and a vast range of Earth observation, weather, and communications satellites. LEO is also where most space debris is concentrated, because LEO is where most of the activity has historically occurred. The middle layer, medium Earth orbit or MEO, extends from roughly 2,000 kilometers to 35,786 kilometers. The GPS constellation orbits at about 20,200 kilometers. The European Galileo navigation system is also in MEO. This region has less total debris than LEO but contains significant hazards, particularly in the radiation belts that trap energetic particles from the Sun and the galaxy. At exactly 35,786 kilometers above the equator is the geostationary belt, where satellites orbit at the same angular velocity as Earth rotates, appearing stationary above a fixed point on the surface. This is where weather satellites, broadcast communication satellites, and many military intelligence assets live. The geostationary belt is a finite resource. Only one satellite can occupy any given slot in the belt without interfering with its neighbors, and the number of useful slots is limited by the geometry of the orbit and the radio frequencies available. Above geostationary orbit, in what is called the graveyard or disposal orbit region, is where old geostationary satellites are supposed to be sent to die. This concept of managed disposal above GEO is one of the better ideas in space debris management. But as we will examine in detail, it has been applied inconsistently and is no longer adequate for the scale of the problem. The total mass of human-made objects in Earth orbit is estimated at approximately 9,000 metric tons. That number is staggering in its absolute scale. It represents the accumulation of 67 years of rocket launches, satellite deployments, rocket stage separations, mission-related hardware jettisons, explosions and collisions. 9,000 metric tons of metal and composite material orbiting Earth at velocities between 7 and 8 kilometers per second in LEO, gradually spreading and fragmenting, and in some cases colliding with each other to produce new debris. The tracked object count grows year over year, not primarily because we are launching more objects, though we are, but because objects that were once intact are breaking apart, each breakup creating hundreds or thousands of new tracked objects where there was one before. Every breakup event is a net multiplication of the hazard. The untracked object population is growing faster than the tracked population, because every breakup generates many more small fragments than large ones, and small fragments escape the resolution of ground-based radar surveillance. An object smaller than roughly 10 centimeters in LEO and smaller than roughly 1 meter in GEO is functionally invisible to the space surveillance network. It exists. It poses a real hazard. We cannot see it. This is the environment that a satellite enters when it dies, not empty space. A complex, layered, partially visible, partially invisible, hazardous environment that it will inhabit, passively, for years or decades or centuries, depending on where in that environment it is located. Understanding the inventory is the prerequisite for understanding the problem, but the inventory itself does not tell you how any particular object got into the shape it is in. For that, you need to understand how satellites actually die. Satellites die in several distinct ways, and the way a satellite dies determines what it becomes afterward. The most common cause of satellite death is fuel exhaustion. Most satellites use chemical propellant, either hydrazine for simple thrusters or a combination of liquid fuels for larger propulsion systems, to maintain their orbits, to point their instruments and antennas, and to conduct the small maneuvers that keep them in the right position relative to Earth and relative to other satellites in their constellation. When the propellant runs out, the satellite can no longer be controlled. It cannot maintain its attitude, the orientation of its body in space. It cannot boost its orbit to compensate for atmospheric drag. It cannot conduct collision avoidance maneuvers. It becomes an uncontrolled mass in orbit, subject only to the forces acting on it from outside. Some satellites carry enough propellant to conduct a controlled deorbit burn at the end of their mission, directing themselves into an atmospheric re-entry. Many do not. Many are designed with just enough fuel to last their planned operational lifetime, with no reserve for end-of-life maneuvers. This was not short-sightedness on the part of the engineers who designed them. It was a rational response to the engineering reality that propellant is heavy. Heavy things are expensive to launch, and in the early decades of the space age, nobody had a clear sense of how serious the debris problem would become. The second major cause of satellite death is power system failure. Satellites generate electricity from solar panels, and they store electricity in batteries for use during the periods when they are in Earth's shadow. Solar panels degrade over time as they are bombarded by radiation from the sun and from the Van Allen belts. The silicon cells lose efficiency, the surface coatings become discolored and reflect less light. The electrical connections fatigue and develop resistance. After 10 or 15 or 20 years, a solar panel that once generated a kilowatt may generate only half that or less. Batteries degrade even faster. The lithium-ion or nickel-hydrogen batteries used in most modern satellites can sustain only a limited number of charge and discharge cycles before their capacity diminishes irreversibly. A battery that could store enough energy to power a satellite through a 45-minute eclipse period may after 10 years be able to store only half that much, leaving the satellite without power for critical systems during every orbit through Earth's shadow. When the battery fails completely, the satellite loses power during each eclipse and its computers reset, losing configuration. Eventually, a power failure that the satellite cannot recover from occurs, and the satellite goes permanently dark. A third cause is attitude control failure. A satellite knows where it is pointing through a combination of star trackers, Earth sensors, gyroscopes, and sun sensors. It corrects its pointing using reaction wheels, tiny spinning masses whose angular momentum counteracts the satellite's own tendency to drift. Reaction wheels are mechanical devices with bearings and motors, operating continuously in the vacuum of space at extreme temperatures, and they wear out. When a reaction wheel fails, the satellite must use propellant thrusters to compensate, which accelerates propellant consumption. When multiple wheels fail, or when thrusters prove insufficient to control the satellite's tumble, the satellite loses attitude control and can no longer point its antennas at Earth or its solar panels at the Sun. A satellite that cannot point its solar panels at the Sun cannot charge its batteries. A satellite that cannot charge its batteries cannot operate. The spiral from attitude control failure to total loss of the satellite can happen quickly. There are rarer but spectacular causes of satellite death. Direct collision with another tracked or untracked object. Damage from solar particle events so intense they overwhelm the radiation shielding of the satellite's electronics. Partial decompression of a pressurized component causing structural damage. Software errors and critical firmware that cause an unrecoverable fault in the onboard computers. And sometimes, simply, a failure mode that nobody anticipated, in a component that had never failed in testing or in previous missions, in an environment that no ground test can fully replicate. The failure modes of satellite systems deserve detailed examination because they follow documented patterns that reveal something about the gap between designed lifetime and actual fate. Battery explosions are among the most dramatic and consequential failure modes of dead satellites. When a battery-powered satellite loses its solar charging ability, the internal chemistry of the battery may enter a state where it poses an explosion risk. Lithium-based and nickel-cadmium batteries can both pose explosion risks when deeply discharged and then recharged, or when subjected to extreme temperature cycling. A battery explosion on a dead satellite in orbit is called a fragmentation event. It produces a cloud of fragments at the orbit of the original satellite. The fragments range from large pieces that can be tracked to tiny shards of battery casing that are far below the tracking threshold. Battery fragmentation events have been documented multiple times in the history of spaceflight and are believed to be responsible for a significant fraction of the untracked debris population. The risk of battery explosions from dead satellites has been recognized for decades, and modern satellite designs typically include provisions to discharge batteries completely and vent remaining pressurized gases at the end of life, reducing the explosion risk. But the fleet of dead satellites currently in orbit includes many that predate these design practices and that pose ongoing fragmentation risks. Envisat, the large European Earth observation satellite that failed unexpectedly in 2012, with approximately 8 tons of mass in a 790-kilometer orbit, carries batteries, pressurized tanks, and other energy-storing components that pose a fragmentation risk for the decades until it naturally decays from orbit. Thermal cycling fragmentation is a slower process but an important one. Objects in low Earth orbit experience extreme temperature swings on every orbit. On the sunlit side of Earth, exposed surfaces can reach 120 degrees Celsius. In Earth's shadow, the same surfaces cool to -100 degrees Celsius. The cycle of heating and cooling, every 90 minutes at typical LEO orbital periods, produces thermal stress in materials. A dead satellite experiences this cycling with no mitigation. The thermal cycling works steadily to degrade structural integrity, producing a gradual shedding of small pieces that join the debris environment as tiny, untracked objects. The cumulative effect over decades of dead satellites is a background contribution to the sub-centimeter debris population that accumulates silently and invisibly. Outgassing is another subtle but real contributor. Many satellite materials contain absorbed gases that are slowly released in the vacuum of space. Plastics, adhesives, and composite materials all outgas at rates that are measurable but not dramatic. As these gases escape from dead satellites, they can generate small thrusts that alter the orbit in unpredictable ways and create micro-debris from particles carried along in the escaping gas. What happens immediately after a satellite fails depends on how it fails. If the failure is gradual, through the slow decline of power or propellant reserves, the satellite typically passes through an operational twilight period during which engineers on the ground scramble to preserve the most critical functions. Unnecessary systems are shut down to extend the power budget. Mission operations are reduced. Communication sessions are shortened. Every kilogram of propellant is managed with increasing care. Ground controllers often have some advance warning of imminent satellite failure through the telemetry the satellite transmits. Voltage readings trend downward, thruster performance degrades, battery depth of discharge increases. The satellite in its final weeks is like a patient whose vital signs are declining and whose doctors can observe the decline in real time but cannot reverse it. When the satellite crosses the threshold into true uncontrollability, ground controllers lose the ability to send meaningful commands. The satellite may still transmit garbled or degraded telemetry for a period, giving operators a view of its deteriorating state. Eventually, even that ceases, and the satellite is silent. What the satellite becomes at that moment is a piece of space debris, not in the abstract or the legal sense, though those classifications apply as well. In the physical sense, a mass of metal and composite material and electronics and residual propellant moving at orbital velocity in a specific orbit, subject to the natural forces acting on it. And it is those natural forces that determine what happens next. The fate of a dead satellite is almost entirely determined by one number, its orbital altitude. This is because the primary force that eventually removes objects from orbit around Earth is atmospheric drag, and atmospheric drag decreases exponentially with altitude. At 300 kilometers altitude, the atmosphere is thin but measurable, and the drag force on a satellite is enough to cause orbital decay over weeks to months. At 600 kilometers, the same satellite would take years to decades. At 800 kilometers, centuries. At 1,000 kilometers, tens of thousands of years. At geostationary orbit, 35,786 kilometers, there is essentially no atmospheric drag at all. An object placed in geostationary orbit today will, barring perturbations from the Moon's gravity and solar radiation pressure, remain in an orbit that is recognizably geostationary for billions of years. The atmosphere does not end at a sharp boundary. It tapers off gradually into the extreme vacuum of space, with density decreasing by roughly an order of magnitude for every 100 kilometers of altitude in the upper thermosphere and lower exosphere. There is measurable gas all the way to several thousand kilometers, though the mean free path between molecular collisions at those heights is measured in kilometers rather than nanometers. The specific mechanism of atmospheric drag is molecular. Gas molecules at orbital altitudes are sparse, but they still collide with the surface of a satellite. Each collision transfers a tiny amount of momentum. At orbital velocities of 7 or 8 kilometers per second, these collisions happen frequently enough, even in the thin upper atmosphere, to cumulatively rob the satellite of orbital energy. As the satellite loses energy, it drops to lower altitudes. As it drops to lower altitudes, the atmosphere is denser and the drag increases. The descent accelerates. The satellite spirals inward faster and faster until it hits the denser lower atmosphere and begins to heat from aerodynamic compression. For most small and medium-sized satellites, this heating is sufficient to completely destroy the object. The satellite begins to tumble and fragment. Individual components break off and heat and ablate. Aluminum melts and boils away. Composites char and disintegrate. The satellite that once was a functioning machine becomes, over the course of minutes, a shower of vapor and small molten droplets that cool and solidify in the upper atmosphere and drift down over years as microscopic metallic particles. But not all of it survives re-entry. A fraction of a satellite's mass, typically between 10 and 40% depending on the satellite's design and the composition of its components, can survive to the ground. Stainless steel tanks, titanium components, and dense optical elements can survive the thermal loads of re-entry intact enough to reach the ground. Re-entries over the ocean, which covers 70% of Earth's surface, typically go unnoticed. Re-entries over populated areas are rare but happen, and occasionally produce visible fireballs that generate news coverage. The altitude question determines not just how quickly a dead satellite decays, but also what it does during the intervening period. A satellite in a relatively low orbit, below about 600 kilometers, will decay naturally in a reasonably short time. The definition of reasonably short depends on your perspective. In human lifetime terms, decades can feel like a long time. In terms of the accumulation of hazardous debris, decades during which a dead tumbling satellite can have multiple close approaches to active satellites and potentially collide with other debris to produce new fragments, decades is not short at all. A satellite in the 600 to 2,000 kilometer range presents a more serious long-term problem. The orbital lifetime at these altitudes ranges from decades to centuries. Satellites that die in this altitude range are debris hazards for a very long time. This is precisely the altitude range where many of the most consequential satellite constellations are being deployed, including the dense Starlink network and other broadband internet satellite systems. A satellite above 2,000 kilometers, in the heart of the radiation belts or in MEO, can remain in orbit for thousands of years. GPS satellites at 20,200 kilometers will, if they die in their operational orbits without being deorbited, remain as debris for tens of thousands of years. This is a timescale that is meaningless in terms of human institutional planning and deeply meaningful in terms of the long-term hazard to the orbital environment. The specific altitude of 800 to 1,000 kilometers deserves detailed attention because it is where the consequences of past decisions are most acutely felt and where the current trajectory of the debris problem is most clearly visible. This altitude range was a preferred location for Earth observation satellites for technical reasons that made it attractive long before the debris consequences were well understood. At 800 to 1,000 kilometers, the atmosphere is thin enough that satellites do not experience meaningful drag and can operate for years or decades on modest propellant budgets. The altitude is low enough that the resolution of optical instruments is sufficient for the kinds of Earth observation missions that agencies wanted to conduct. Mapping forests and ice sheets, monitoring agricultural conditions, tracking disaster zones, conducting military reconnaissance. Over the decades, hundreds of satellites were placed in this altitude range. Early weather satellites, military reconnaissance satellites, scientific Earth observation platforms, and with them, an accumulating population of spent rocket upper stages, mission hardware jettisoned after use, and eventually the debris from breakup events. What makes the specific events of the Chinese ASAT test and the Iridium-Kosmos collision particularly concerning is not just the number of fragments they produced, but the altitude at which those fragments reside. At 789 kilometers, Iridium-Kosmos debris will take decades to naturally decay. At 865 kilometers, Fengyun 1C debris will take centuries. These fragments are long-term residents of the altitude range, sharing it with dozens of active operational satellites. The specific mechanism by which the Kessler threshold is approached in this altitude range is not primarily the dramatic collision events but the slow accumulation of smaller ones. Untracked fragments strike operational satellites, generating new fragments. Dead satellites strike other dead satellites, generating new fragments. Thermal cycling and battery explosions generate new fragments. Each new fragment is a new collision hazard. Each new collision hazard generates more fragments. The range of estimates from credible researchers about when or whether the 800 to 1,000 kilometer altitude band has crossed the Kessler threshold is not reassuring. The most optimistic estimates suggest the threshold is still decades away if aggressive debris mitigation measures are implemented. The most pessimistic suggest we may have already crossed it in this specific altitude range. The uncertainty reflects genuine uncertainty in the collision cross-sections of irregular debris objects and in the distribution of debris sizes in the untracked population. The specific situation of ENVISAT illustrates the risk in concentrated form. This European Earth observation satellite, approximately 8,200 kilograms in mass, failed unexpectedly in 2012 and has been tumbling uncontrolled in a 790-kilometer orbit ever since. Its mass makes it by far the largest single debris object in the 800-kilometer altitude band. A collision with another object at orbital velocities would generate a debris cloud far larger than the Iridium-Kosmos collision, which involved objects of roughly 600 and 900 kilograms respectively. ENVISAT will remain in this orbit for an estimated 100 to 150 years. That is a century of a bus-sized tumbling object in the most hazardous part of the orbital environment, with no active removal capability currently funded or operational. And then there is geostationary orbit, where the fundamental physics of the situation is profoundly different from every other altitude. At 35,786 kilometers, an object that stops under power becomes, for all practical purposes, a permanent resident of the geostationary belt. It will drift slowly from its station-kept position, because without thrusters, it can no longer resist the small perturbations from the Moon's gravity and solar radiation pressure that constantly nudge geostationary satellites off their assigned positions. Over months, a dead satellite in the geostationary belt will drift along the orbit, approaching other satellites and potentially interfering with their operations. Over years, it will have traversed portions of the belt, occupying space that other satellites need. This is not a theoretical problem. There are currently more than 750 known objects in the geostationary belt that are not functional satellites. They include old communication satellites from the 1960s, 1970s, 1980s, and every decade since. Some of them are intact but dead. Some of them have broken apart into multiple pieces. All of them are essentially permanent. The dead objects in geostationary orbit are not going anywhere. Not in any human-relevant timescale. Not in any geological timescale. The Moon's gravity and solar radiation pressure will eventually perturb them into slightly different orbits over millions of years. The geostationary orbit is effectively self-cleaning on this timescale, only in the sense that individual objects will eventually be perturbed away from the exact geostationary altitude, but they will remain in the general region of geostationary space indefinitely. The specific concern about geostationary orbit is not collision risk in the same direct sense as in LEO. The geostationary belt is a ring 265,000 kilometers in circumference. The spacing between objects in the belt, even with hundreds of dead satellites present, is generally large enough that direct collisions are unlikely, except for objects that drift into close proximity over time. The concern is frequency interference, the radio signals from dead satellites that may still have leaking power or reflective antenna surfaces that can disrupt the communications of active satellites in adjacent slots. And the concern is the long-term trend. As more satellites die and join the population of belt debris, the risk of eventual collision or interference grows. The altitude hierarchy of orbital fate is the foundational fact of the space debris problem. Everything else, the policy debates, the technical solutions, the urgency calculations, is downstream of this fundamental physical reality. Where you put something in orbit determines how long it stays there, and in many cases how long it stays there is a very long time indeed. In 1978, a NASA scientist named Donald Kessler published a paper with his colleague Burton Coeur-Palais in the Journal of Geophysical Research. The paper was titled Collision Frequency of Artificial Satellites, the Creation of a Debris Belt. It described something that had not yet happened, but that the authors argued was inevitable if the population of objects in Earth orbit continued to grow without limit. The mechanism Kessler and Coeur-Palais described is straightforward in principle and devastating in implication. As the number of objects in orbit increases, the probability that any given object will collide with another object also increases. When two orbital objects collide, both are destroyed and replaced by a large number of smaller fragments. Each fragment has its own orbital parameters. Most of the fragments remain in roughly the same altitude range as the original objects. These fragments are themselves collision hazards for the other objects sharing that altitude range. As the fragment population grows, the collision rate increases. As the collision rate increases, the fragment population grows faster. The process is self-reinforcing. If the density of objects in a particular orbital shell exceeds a critical threshold, this positive feedback loop becomes runaway. Even if humanity stops launching satellites entirely, the existing population of objects would generate enough collisions to produce enough new fragments to sustain and accelerate the cascade. The orbital shell would become progressively more hazardous until it was effectively impassable. Active satellites would be destroyed. New satellites could not be placed there. The shell would be, for practical purposes, permanently lost. Kessler called this phenomenon collisional cascading. It became known as the Kessler syndrome. For years, Kessler's scenario was treated as a distant theoretical concern. The debris population was sparse, the collision rate was low, the cascade was something to worry about in the future, not the present. Then specific events began to make the concern more immediate. In July 1996, the French spy satellite Ceres was struck by a fragment of an Ariane 1 rocket that had exploded in 1986. This was the first confirmed collision between a tracked object and a catalogued debris fragment. The satellite survived, but its attitude control boom was severed. In January 2007, the Chinese military deliberately destroyed one of its own weather satellites, the Fengyun 1C, with a kinetic interceptor missile at an altitude of approximately 865 kilometers. The destruction produced an estimated 3,000 tracked debris fragments and an unknown number of smaller untracked fragments, scattered across a range of altitudes that overlapped with many operational satellites. The Chinese ASAT test was the largest single debris-generating event in the history of spaceflight. The fragments will remain hazardous for decades to centuries. In February 2009, a defunct Russian communications satellite called Cosmos 2251 collided with an operational American Iridium communications satellite at an altitude of approximately 789 kilometers. The collision was the first accidental hypervelocity collision between two intact satellites in orbit. It produced more than 2,000 tracked fragments between the two satellites and destroyed the Iridium satellite completely. In November 2021, the Russian military destroyed one of its own defunct reconnaissance satellites, Kosmos 1408, with a kinetic interceptor. The event produced approximately 1,500 new tracked debris fragments at an altitude of roughly 500 kilometers. The crew of the International Space Station was forced to shelter in their docked Soyuz and Dragon capsules for hours, while the orbital debris cloud passed through the station's orbital altitude. These specific events were notable and newsworthy, but they were not by themselves what makes the Kessler syndrome a present rather than a future concern. What makes it a present concern is the ongoing low-level collision rate between objects too small to track and objects too small to be identified in subsequent surveillance. Every year, the debris population in certain orbital shells becomes slightly denser. Every year, the probability of collision events in those shells increases slightly. The trend line points toward a threshold that researchers disagree about the precise location of, but that most agree is at most a few decades away in the most populated orbital shells, if not already behind us in some of them. The 800 to 1,000 kilometer altitude band is considered the region of highest concern. This altitude range is where atmospheric drag is weak enough that objects remain for decades or centuries. It is where the Chinese ASAT test debris and the Iridium-Kosmos collision debris are concentrated. It is where many Earth observation and remote sensing satellites orbit, and it is, by most analyses, the altitude range closest to or perhaps already past the Kessler threshold. The phrase already past is disputed and important. A group of researchers at NASA's Orbital Debris Program Office have published analysis suggesting that the existing debris population in certain altitude bands is sufficient to sustain a slow cascade without any new launches. The cascade, in this interpretation, has already begun. It is not the rapid, dramatic scenario of science fiction, where orbital space becomes impassable in days. It is a slow build-up of fragments over decades, a gradual increase in collision probability, an incremental degradation of the orbital environment. The gradual version is, in some ways, more dangerous than the rapid version. A rapid catastrophe would be unmistakable. The orbital environment would become visibly hazardous, and there would be a clear, immediate crisis driving immediate response. A slow cascade is ambiguous. The debris density increases year over year, but so does the capability of surveillance systems. The collision rate increases, but it increases slowly enough that individual events are separated by years. The urgency is harder to communicate when each year looks only slightly worse than the last. What the Kessler syndrome ultimately represents is not a single dramatic event, but a direction. If the trend continues, specific orbital shells will become progressively less accessible. Operating a satellite in a progressively more hazardous environment requires more collision avoidance maneuvers, more propellant, more ground operations attention, more satellite insurance cost, more operational interruption. At some point, the cost exceeds the value, and the shell is effectively lost to operational use. The shell does not become impassable overnight. It becomes uneconomical, and then impractical, and then impossible. We do not know precisely where that threshold is for each orbital altitude, but we know the direction. And we know that the events of the last 20 years have moved us closer to it, not further from it. The space industry recognized the debris problem decades ago and developed solutions that were, in their time, reasonable responses to the scale of the problem at that time. Those solutions are the graveyard orbit and the controlled deorbit. The graveyard orbit applies to geostationary satellites. The idea is simple. When a geostationary satellite reaches the end of its operational life, rather than leaving it in the geostationary belt where it will interfere with active satellites, the operator uses the last of the satellite's propellant to boost it into a higher orbit, approximately 300 kilometers above geostationary altitude. At this slightly higher altitude, there is less commercial value and less operational activity. The dead satellite can drift harmlessly in this disposal orbit. The graveyard orbit concept emerged in the 1970s and was formalized as a recommended practice by international space agencies in subsequent decades. By the 1990s, most responsible operators of geostationary satellites were following it, using roughly 10 to 15% of a satellite's total propellant budget for the final graveyard boost maneuver. The concept was sound and remained sound for individual satellites. The problem is that the graveyard orbit is filling up. There are currently more than 300 objects in the geostationary graveyard. the region between roughly 36,100 and 36,500 kilometers altitude. These objects include intact dead satellites, partially broken up satellites, and fragments from various events. The graveyard is not yet full in any meaningful sense. The volume of space is large, and the current density of objects is still low enough that collisions are rare. But the graveyard is cumulative. Objects go in and do not come out. Every year, more dead satellites are boosted to the graveyard. The population grows indefinitely. The fundamental limitation of the graveyard orbit as a solution is that it is a transfer of the problem, not a solution to it. The graveyard orbit is itself an orbital altitude in which objects persist essentially permanently. Moving dead satellites to the graveyard reduces the hazard they pose to active satellites in the geostationary belt, but it does not remove the objects from orbit. It places them in a region where, centuries from now, the density may be high enough to generate collisions that produce fragments that migrate back into the geostationary belt. The graveyard is a landfill, not a disposal facility. For low Earth orbit, the standard recommended practice is the 25-year rule. Satellites should be designed to deorbit within 25 years of the end of their operational life, either through propulsive deorbit maneuvers or through naturally decaying orbits at altitudes low enough that atmospheric drag achieves the re-entry within the 25-year window. The 25-year rule has serious problems. First, it is a guideline, not a law. It was established by the Interagency Space Debris Coordination Committee, a multinational body that coordinates debris mitigation practices among the world's space agencies. The guideline was adopted as a recommended practice, not a legally binding obligation. Individual countries may adopt it as law within their national regulatory frameworks, but the Outer Space Treaty, the foundational document of international space law, does not require it. Many operators have followed it, many have not. Second, even perfect compliance with the 25-year rule is insufficient to stabilize the debris environment in many orbital shells. Analysis by researchers at NASA and ESA has shown that even if every future satellite perfectly complied with the 25-year rule, the total debris population in the most congested orbital shells would continue to grow, because the rate of new debris generation from collisions among existing objects exceeds the rate of natural decay and compliance-driven deorbit. Third, the compliance rate with the 25-year rule has historically been poor. Surveys of satellites that have reached their end of life have found that a significant fraction, in some studies more than half, do not achieve compliance with the 25-year rule. Some fail to deorbit because the satellite fails before a deorbit maneuver can be conducted. Some fail because operators run out of propellant before completing the deorbit. Some fail because the satellite's orbit was designed for a lifetime of operation at an altitude where 25-year natural decay is not achievable, and no propulsive deorbit was planned. Some fail simply because the operator does not prioritize the end-of-life maneuver. The recognition of the inadequacy of the 25-year rule has led to growing pressure for stricter standards. In 2022, the US Federal Communications Commission adopted a new rule requiring most US-licensed satellites in LEO to deorbit within 5 years of the end of their operational life, a significant tightening from the previous 25-year guideline. Other national regulatory bodies are developing similar requirements. The trend towards stricter deorbit requirements is clear, but the international landscape remains fragmented, with different countries applying different standards and no universal enforcement mechanism. There is one more dimension of the dead satellite problem that the graveyard orbit and deorbit rules do not address at all: the satellites that die before they can be disposed of. A satellite that fails unexpectedly, through a sudden component failure rather than the gradual decline that allows for planned end-of-life disposal, is left in whatever orbit it occupied at the time of failure. This may be an orbit for which natural decay takes decades or centuries, or is essentially non-existent. The operator may have no way to conduct a deorbit maneuver because the satellite's propulsion system has failed. The satellite becomes debris immediately, in whatever orbit it was in, with no disposal option available. This is not a rare scenario. Satellite failures are common. The most comprehensive studies suggest that roughly 1 in 10 satellites fails before its planned operational life is complete, through some form of anomaly that leaves it unable to perform end-of-life disposal. These unexpected failures produce some of the most problematic debris. objects in orbits for which there is no reasonable near-term natural decay, placed there without any disposal plan because the disposal was planned for a future that the satellite never reached. The solutions we have, graveyard orbits and deorbit requirements, work when satellites die as planned. They do not help when satellites die unexpectedly. And that gap between the expected and the unexpected, between the planned and the anomalous, is where a significant fraction of the debris problem actually lives. The specific trajectory of active debris removal technology is worth examining closely, because the gap between what has been demonstrated and what would be needed is very large, and understanding the gap is necessary for understanding the timeline of any realistic solution. The most fundamental challenge of active debris removal is approaching and capturing an object that is tumbling at uncontrolled angular velocities in an environment filled with other debris hazards. A dead satellite is not cooperative. It has no docking ports designed for external capture. It has no attitude control to stop its tumbling. Its solar panels and antenna structures create complex geometries that make approach trajectories hazardous, and it is surrounded by other debris, some tracked and some not. The ClearSpace 1 mission, targeting a spent rocket body in the 800-kilometer altitude range, represents the first serious operational test of debris capture technology. The target, the Vesper adapter used in the Proba-V mission, is a relatively compact object of approximately 100 kilograms. The ClearSpace spacecraft will use a claw mechanism to capture the target, requiring a high-precision rendezvous and approach operation at close range near a tumbling object. The technical challenge of the capture operation is formidable. The rendezvous phase, approaching to within meters of the target, requires precise relative navigation using cameras and LiDAR sensors to determine the target's attitude and angular velocity. The capture phase requires timing the approach precisely to avoid impact with protruding structures on the tumbling target. The post-capture phase requires managing the angular momentum transferred to the combined spacecraft plus debris system during the capture, which can cause the combined vehicle to spin up if not properly managed. All of these operations must be conducted autonomously, or with significant ground delay, because ground operators cannot react in real time at orbital velocities. The software that guides the spacecraft through the approach and capture sequence must be reliable enough to handle the range of target attitudes and tumble rates it might encounter, without a human controller available to intervene if something unexpected occurs. The ClearSpace 1 mission is a demonstration, not an operational system. Even if it succeeds perfectly, removing one piece of debris from orbit proves that the technology works, but does not constitute a debris removal program. Scaling from one demonstration to the hundreds or thousands of removals required to meaningfully stabilize the debris environment requires not just proven technology, but a delivery system, a business model, and an international authorization framework. None of these exists. The Astroscale LSAD demonstration revealed the depth of the cooperation problem. The system worked as designed. It successfully demonstrated rendezvous, proximity operations, and magnetic capture of a target satellite. But the requirement that the target be pre-equipped with a magnetic docking plate illustrates the core challenge of the broader debris population. Millions of pieces of existing debris have no docking plates, no cooperative features, no design elements intended to facilitate future capture. Removing them requires developing capture mechanisms that can work with uncooperative, irregularly shaped, tumbling objects of varying size and composition. Research programs are developing such mechanisms: harpoons, nets, gecko-inspired adhesive grippers, robotic arms with force feedback control, electrostatic grippers. Each has been tested at subscale or in ground simulations. None has been demonstrated operationally against a real large uncooperative debris object in orbit. The path from laboratory demonstration to operational capability for uncooperative debris capture is measured in decades, not years. The logical response to the inadequacy of passive disposal strategies is active debris removal, sending dedicated spacecraft to physically retrieve or redirect dead satellites and debris. Active debris removal is technically feasible. The physics are understood. Several different approaches have been proposed and tested at various stages of maturity. Spacecraft have been demonstrated in orbit that can approach, capture, and manipulate other objects. The engineering is hard but not impossible. The economics are the fundamental problem. Removing a single large piece of debris from orbit, like a dead satellite or an upper stage rocket body, costs an estimated tens to hundreds of millions of dollars with current technology. This price reflects the cost of designing and launching a specialized spacecraft, the complexity of approaching and capturing an object that is tumbling at potentially several degrees per second, the propulsion required to deorbit the captured object, and the operational costs of the mission over its duration. At that price, removing even 1% of the 2,000 largest objects in orbit, which most researchers agree is approximately the minimum required to stabilize the debris environment in the most critical orbital shells, would cost tens to hundreds of billions of dollars. There is currently no business model that makes this expenditure attractive to a private operator. The party that removes debris captures only a tiny fraction of the benefit, because the stabilized orbital environment is a public good available to every satellite operator. The other satellite operators who benefit from a cleaner orbital environment do not pay the party who cleaned it. This is the classic tragedy of the commons. The orbital environment is a shared resource. Each operator who uses it without contributing to its maintenance captures private benefit, while the cost of degradation is distributed across all users. Each operator who invests in debris cleanup pays private costs, while the benefit is distributed across all users. The incentive structure actively discourages the behavior that would benefit the collective. Recognizing this, several companies and research organizations have pursued active debris removal, despite the unfavorable economics, funded by government contracts and research grants rather than commercial revenue. The European Space Agency contracted with ClearSpace, a Swiss startup, for a mission called ClearSpace 1. The mission objective is to capture a spent rocket body from an ESA mission called Proba V, a roughly 100-kilogram object in an orbit of about 800 kilometers. The ClearSpace 1 spacecraft, designed to use a claw-like mechanism to capture the target and then deorbit both spacecraft together, was originally planned for launch in 2025. It has since been delayed. If it launches and succeeds, it will be the first operational demonstration of active debris removal. Astroscale, a Japanese startup with offices in multiple countries, developed and tested a system called ELSA-D for end-of-life services by astroscale demonstration. The ELSA-D mission launched in 2021 and demonstrated key technologies including rendezvous, proximity operations, and magnetic capture of a target satellite that had been equipped with a docking plate during manufacture. The demonstration showed that the approach technology works. It also illustrated the fundamental challenge. ELSA-D could capture only satellites that had been pre-equipped with a magnetic docking plate before launch. The vast majority of existing debris has no such equipment. The problem of capturing uncooperative targets, objects that were not designed with capture aids and that may be tumbling unpredictably, is the central technical challenge of debris removal. Various approaches have been tested at smaller scales. Remove Debris, a mission from the University of Surrey, tested a net and a harpoon in orbit in 2018. The net test successfully captured a small target satellite. The harpoon successfully penetrated a foam target. Neither technology has been tested against a real large tumbling debris object. Other proposed approaches include laser ablation, using a ground-based or space-based laser to vaporize a small amount of material on the debris surface, generating a thrust that gradually changes the debris orbit over many passes. Ion beam shepherd, using the exhaust from an ion thruster to push a piece of debris without physically contacting it, a potentially attractive approach for debris that is spinning too fast to safely capture. Electrodynamic tethers, using a long conducting wire in the magnetic field of Earth to generate a braking force. Each of these approaches has been analyzed theoretically, and some have been tested in limited demonstrations. None of them has been deployed in an operational debris removal mission. The gap between the demonstrated technologies and the operational deployment of active debris removal at the scale required to actually stabilize the orbital environment is very large. We know how to do the basic operations: approach, rendezvous, capture in some configurations, and deorbit. We do not have a business model that makes doing these operations at scale economically viable without substantial ongoing government subsidy. And we do not have an international agreement that establishes who is responsible for the cost of cleanup, who has the authority to remove another nation's space objects, or what legal framework applies when a removal mission causes damage. The legal dimension is genuinely complex. Space objects remain the property of the nation that launched them under the Outer Space Treaty. A private company from country A cannot simply go up and remove a dead satellite from country B without some form of authorization from country B. Getting that authorization requires diplomatic engagement and legal agreements that do not currently exist in any systematic form. The practical mechanics of international debris removal are not just technically hard, they are politically hard in ways that technical progress cannot resolve. The specific scenario that the debris researchers most fear connects the near-term trend to the long-term consequence in a way that is worth describing explicitly. The new generation of large broadband satellite constellations, of which Starlink is the most prominent but not the only example, represents a fundamental change in the population of active satellites in low Earth orbit. In 2019, there were roughly 2,000 active satellites in all of Earth orbit. By 2024, that number had grown to more than 9,000, with Starlink satellites alone numbering more than 6,000. Plans for SpaceX's Starlink, Amazon's Kuiper, the OneWeb constellation, and various national broadband satellite programs envision tens of thousands of additional satellites over the next decade. These constellations are designed for low altitudes, typically below 600 kilometers, specifically because atmospheric drag at those altitudes ensures that failed satellites decay and re-enter within a few years to a decade. This is the right altitude choice from a debris mitigation perspective. The designers understood the Kessler problem and specifically chose low altitudes to avoid contributing to the long-term debris accumulation that threatens higher orbital shells. But even at low altitudes, the sheer scale of the constellations creates new challenges. A fleet of 10,000 satellites with a failure rate of 1% per year generates 100 failed satellites annually. At low altitudes, those 100 satellites will re-enter within years, not decades. But in the period between failure and re-entry, each failed satellite is an uncontrolled object in the most densely populated region of low Earth orbit, requiring collision avoidance maneuvers by active satellites and increasing the probability of collisions that generate new untracked debris. The specific concern is not any single large collision event, but the steady-state failure rate of large constellations creating a permanent background of uncontrolled objects in low altitudes. Even if the failure rate is well below 1%, the absolute number of failed satellites from a constellation of tens of thousands is not small. Managing this population requires tracking, collision avoidance planning, and eventual collision events that generate debris at low altitudes. Low-altitude debris is not the same problem as high-altitude debris. At 500 to 600 kilometers, debris decays within years to a decade, so the debris population is self-cleaning on a timescale that is short compared to the Kessler timescale at 800 to 1,000 kilometers. But the decay is not instantaneous, and the debris generated by constellation failures accumulates in the short term. The specific risk is not a Kessler cascade at 500 to 600 kilometers, where the self-cleaning timescale is too short for cascading to be likely. The risk is cumulative debris generation that makes collision avoidance more burdensome and more expensive for all operators in the altitude range, that occasionally produces larger collision events that generate debris with longer decay times than expected, and that normalizes a higher level of debris in low altitudes in ways that complicate both operations and future removal. The response to this concern has been regulatory. The USFCC's adoption of the 5-year deorbit rule, stricter licensing requirements for large constellations, and growing international pressure for compliance with deorbit standards. These regulatory responses are meaningful. They change the incentive structure for constellation design in the right direction. But they are not sufficient, and compliance is not universal, and the gap between what regulations require and what perfect debris hygiene would require remains significant. The political and legal landscape of space debris reveals something fundamental about the limits of international governance when individual and collective interests diverge sharply. The Outer Space Treaty of 1967 is the foundational document of international space law. Negotiated during the Cold War as part of the effort to prevent the militarization of space, it establishes several key principles. Space is the province of all mankind. Nations cannot claim sovereignty over the moon or other celestial bodies. Nations are responsible for the activities of their national space operators, including commercial operators. Nations retain jurisdiction and control over objects they launch, even when those objects are in space. The last two principles create the legal architecture of the debris problem. A nation is responsible for its satellites. A nation retains ownership of its satellites. This means that if another nation wants to remove a dead satellite, even a satellite that poses a hazard to all other users of that orbital altitude, it must first obtain the consent of the owning nation. Removing another nation's satellite without consent could be construed as an act of hostility or at minimum a violation of the satellite operator's property rights. This is not an abstract concern. China and Russia have on multiple occasions expressed suspicion about Western proposals for active debris removal, viewing the development of spacecraft capable of approaching and manipulating other space objects as potential dual-use military capabilities that could threaten their operational satellites. An active debris removal spacecraft is, from a capability standpoint, not so different from an anti-satellite weapon that works by capturing or deorbiting adversary satellites. The technology overlap is uncomfortably close. The Registration Convention of 1975 requires nations to register objects they launch into space, providing basic information to a United Nations registry that is supposed to allow the tracking of who owns what. In practice, the registry is incomplete. Not all nations participate fully, and the data provided is not always sufficient to uniquely identify which specific launch event corresponds to which specific orbital object. The ITU, the International Telecommunication Union, manages the radio frequency coordination that allows satellite operators to use the electromagnetic spectrum without interfering with each other. The ITU processes are relevant to the debris problem because abandoned satellites can interfere with operational satellites' communications if their transmitters are still emitting on registered frequencies. The ITU's procedures for dealing with abandoned spectrum registrations are cumbersome and slow. Beyond these existing frameworks, there is very little international law that directly addresses the space debris problem. There is no treaty requiring satellite operators to design for end-of-life disposal. There is no internationally binding rule about deorbit timelines. There is no international fund for debris cleanup. There is no international body with the authority and resources to conduct or compel debris cleanup. The existing frameworks are the result of negotiations conducted when the debris problem was abstract and theoretical. They are inadequate for the debris problem as it actually exists today. Efforts to update the international frameworks have been ongoing for decades. The IADC, the Interagency Space Debris Coordination Committee, brings together the space agencies of major spacefaring nations to coordinate guidelines. The United Nations Committee on the Peaceful Uses of Outer Space provides a forum for discussion of space governance issues. Various bilateral and multilateral agreements govern specific aspects of space operations. The European Space Agency has published detailed debris mitigation standards. The United States has developed increasingly strict national requirements for debris mitigation and deorbit. But none of these mechanisms adds up to the comprehensive, enforceable international governance that the scale of the problem seems to require. The orbital environment is a global commons. The tragedy of the commons applies precisely when there is insufficient governance, and the governance that exists is voluntary, incomplete, and enforced only by the individual choices of sovereign nations whose primary interest is in maximizing their own use of the orbital environment, not in paying costs to benefit competitors. The new commercial space era has added additional complexity to this already difficult governance landscape. A generation ago, the space operators were primarily national space agencies, large government entities that could be engaged through diplomatic channels, and that had some incentive to participate in international norms as a matter of national reputation. Today, the space operators include hundreds of commercial companies in dozens of countries, ranging from well-capitalized public companies to small startups with uncertain financial futures. A startup satellite operator that launches a constellation of 50 satellites and goes bankrupt 2 years later does not have any mechanism for conducting end-of-life disposal of those 50 satellites. The satellite operator is gone, the satellites remain. The legal responsibility reverts to the nation that licensed the operator. But if that nation lacks the technical capability to conduct deorbit maneuvers and has no contractual relationship with any operator who could, the satellites simply drift. This is not a hypothetical scenario. Several small commercial satellite operators have failed, leaving satellites in orbit with no clear path to disposal. The problem is certain to grow as the commercial space industry continues to expand and more operators enter and exit the market. The political failure of space debris governance is not a failure of anyone's intentions. Most satellite operators, most space agencies, most governments genuinely recognize the problem and prefer a cleaner orbital environment. The failure is structural. It is the gap between what individual rational actors will pay for and what the collective good requires. It is the gap between the power of existing international law and the scale of the problem it needs to govern. It is the gap between the speed of technological change and the speed of diplomatic negotiation. Closing these gaps, if they can be closed, will require either a significant expansion of international space governance or a significant technology cost reduction in debris removal that makes commercial cleanup economically viable. Both are possible in principle. Neither is happening at the pace the problem demands. The graveyard orbit solution reveals something important about the long-term structure of the debris problem. It is a solution that works for the acute problem it addresses, the crowding of the geostationary belt, while creating a deferred version of the same problem at a slightly higher altitude. The concept of a disposal orbit above geostationary is sound as a near-term measure. Moving dead satellites 300 kilometers above the operational belt, where there is less activity and less commercial value, reduces the immediate hazard they pose to active satellites in the geostationary belt. The distance is sufficient that the dead satellites' radio emissions and occasional mechanical debris are less likely to interfere with active operations. But the graveyard orbit is cumulative and permanent. Every geostationary satellite that reaches the end of its life and executes a proper graveyard boost joins a population that can only grow. There is no natural mechanism that removes objects from the graveyard orbit. There is no active removal program. The population of objects in the graveyard orbit will continue to increase as long as humans operate geostationary satellites and follow the recommended disposal practice. The long-term consequence, measured on a timescale of centuries, is a graveyard that accumulates enough objects that collision probability between graveyard objects becomes significant. When two dead geostationary-class satellites collide in the graveyard orbit, the resulting debris is generated at an altitude where it will remain essentially permanently. The debris spreads along the orbital path, creating a diffuse hazard ring above geostationary orbit. Over time, as the graveyard fills and collision events occur, debris from the graveyard region migrates into the geostationary belt altitude through perturbations and the spreading of debris clouds. The graveyard orbit solution converts an acute problem, the crowding of the geostationary belt with dead satellites, into a long-term problem. The slow filling of the graveyard region with dead satellites, and eventually with the debris from their collisions. The acute problem is deferred, but the debt accumulates. The same structural logic applies to the 25-year and 5-year deorbit rules for LEO satellites. A satellite that deorbits within 5 years of mission end is no longer a long-term debris hazard in the altitude range where it operated. But the deorbit requires propellant that must be carried from launch, mass that makes the satellite more expensive to launch, and end-of-a-life operations that require spacecraft capable of executing the maneuver. The regulations can be met through degraded compliance, satellites that technically deorbit within the required time but only barely, spending years in progressively lower orbits before finally re-entering. The regulatory approach to debris management is necessary but insufficient. Regulations reduce the rate of new debris generation per satellite. They do not address the existing debris population. They do not address unexpected failures, and they depend entirely on the willingness of operators in every jurisdiction to comply with enforcement mechanisms that are national in scope in a problem that is inherently international. The close of this mission briefing is not comfortable. There is no satisfying resolution to offer, no moment where the problem turns out to be smaller than feared, or the solution turns out to be closer than expected. The orbital environment above Earth is a resource that was inherited from physics and exploited by technology without adequate planning for its long-term maintenance. The exploitation has been enormously valuable. The satellites that orbit Earth enable GPS navigation, global weather forecasting, international communications, internet access, financial transaction settlement, scientific monitoring of climate and oceans and forests, and 100 other services that have become so deeply woven into the fabric of daily life that their absence would constitute a civilizational disruption. The value of the orbital environment is immense, and the mismanagement of the orbital environment is ongoing. Vanguard 1 is still up there. So is Telstar 1, the first commercial communications satellite, launched in 1962, which stopped working that same year, and has been in orbit for more than 60 years with no function except to continue existing. So are the thousands of rocket bodies and mission hardware fragments and dead satellites, and debris clouds from breakup events that have accumulated since 1957. The accumulation is not slowing. It is accelerating because more is being launched than ever before, and the ratio of active satellites to debris is not improving. The new constellations are changing the character of the problem in ways that are not fully understood. SpaceX's Starlink constellation, which grew from a few hundred satellites to more than 6,000 in a few years, and is planned to expand to tens of thousands, operates at altitudes low enough that natural decay will remove failed satellites within a few years. This is the right altitude choice for exactly this reason. But tens of thousands of satellites in LEO still represent a fundamental change in the density of objects in that environment, and a failure rate of even a small fraction of 1% produces hundreds of dead satellites annually. There is a future in which the problem is solved. In that future, active debris removal technology has matured to the point where large-piece cleanup is economically viable. International governance has evolved to establish clear liability rules and cleanup obligations. Satellite design has shifted toward fully implementing end-of-life disposal as a core requirement rather than a recommended practice. Debris surveillance has improved to the point where objects smaller than a centimeter are tracked, enabling collision avoidance maneuvers for threats that are currently invisible. The Kessler threshold is approached but not crossed, and the debris environment stabilizes rather than cascading. That future is technically achievable. Every element of it involves engineering and policy challenges that are hard but not impossible. The physics permits solutions. The question is whether the human institutions, the economic incentives, the international agreements, and the political will can be assembled in the time available, and there is a future in which the problem is not solved. In that future, the density of debris in the 800 to 1,000 kilometer altitude band continues to increase. Collision events become more frequent. Each collision produces more debris. The probability of subsequent collisions increases. Satellite operators in the affected altitude range begin to pay more for collision avoidance, more for operational interruptions, more for replacement satellites when active ones are destroyed. The cost of operating in certain orbital shells rises to the point where they are no longer economically attractive. Those shells are effectively abandoned to the debris. The lost shells were where scientific observation satellites operated, where small commercial Earth observation satellites operated, where certain communications satellites operated. Those services become more expensive or impossible. The cascading loss of orbital shells would not feel like a single dramatic event. It would feel like a slow increase in operational costs, a slow increase in the frequency of close approaches and debris avoidance maneuvers, a slow disappearance of certain types of satellites from certain altitude ranges. The loss would be gradual enough that it would be easy to deny at each individual step. There is a phrase that Kessler used when describing the possibility of irreversible cascade, a self-sustaining debris belt. The precise words deserve attention. Self-sustaining means the process continues without any new contribution from human activity. Belt suggests something like the asteroid belt, a feature of the solar system that will persist essentially forever. A self-sustaining debris belt in Earth orbit would be a permanent human legacy, as permanent as any geological formation, as permanent as the cities we have built on the continents. We have not yet created a self-sustaining debris belt. The question of whether we will is not a question about physics. The physics is clear enough. It is a question about governance, economics, political will, and the ability of human institutions to act on timescales that the problem demands. The satellites that die today will be in orbit for years or decades or centuries or essentially forever, depending on where they are. They will collide occasionally with other objects. They will produce fragments. Those fragments will collide with other fragments. The process will continue until either the problem is actively managed or it reaches a threshold at which managing it becomes impossible. The window for active management is open. We do not know how long it will remain so. Vanguard 1 is still up there, silently, patient, in the orbit that the physics of 1958 assigned it, a monument of a kind to the beginning of the space age, and a question of a kind about the kind of legacy we are willing to leave in the sky. There is a specific and uncomfortable implication of the debris problem that most discussions avoid, and it concerns not the orbital environment, but the political economy of attention. The orbital debris problem has all the characteristics of problems that human institutions handle poorly. It is diffuse rather than concentrated. It unfolds on timescales longer than political cycles. The costs of inaction accumulate slowly and are hard to attribute to specific decisions, and the parties who bear the greatest responsibility for creating the problem are not obviously different from the parties who would need to fund the solution. Every satellite operator that launches without adequate end-of-life disposal planning contributes to the problem. Every nation that conducts anti-satellite weapons tests contributes dramatically to the problem. Every commercial operator that goes bankrupt leaving satellites in orbit contributes to the problem. Every regulatory body that treats the 25-year rule as aspirational rather than mandatory, contributes to the problem. The responsibility is distributed across decades of decisions by hundreds of actors in dozens of countries, none of whom bears individually obvious responsibility for the cumulative outcome. Concentrated problems with identifiable responsible parties are easier for institutions to address. The factory polluting a specific river can be identified and penalized. The company dumping waste in a specific location can be required to clean it up. The diffuse, cumulative, multi-actor problem of orbital debris does not fit neatly into existing legal and regulatory frameworks that were designed for concentrated, identifiable harms. The analogy to ocean plastic pollution is instructive. Ocean plastic is another diffuse, cumulative, multi-actor problem in a global commons. The harm is real and well documented. The responsible parties are diffuse, individual consumers, manufacturers, waste management systems, shipping operators, and governments in dozens of countries. The cleanup cost is enormous relative to any individual actor's contribution to the problem. The international governance mechanisms are inadequate. The rate of cleanup is running far behind the rate of accumulation. The difference between ocean plastic and orbital debris is the timescale. Plastic degrades over decades to centuries, a long time by human standards but relatively short by institutional standards. Orbital debris at high altitudes persists for centuries to essentially permanently. The ocean plastic problem is bad and getting worse. The orbital debris problem in certain orbital shells is approaching a threshold beyond which it becomes self-perpetuating in a way that no ocean pollution problem has ever been. The urgency of the orbital debris problem, its proximity to irreversibility, is not reflected in the attention and resources currently directed at it. The problem is managed at the margins, through voluntary guidelines and imperfect compliance and modest research programs, while the underlying trend continues in the wrong direction. This is not for lack of knowledge. The knowledge is available. It is for lack of the political and economic mechanisms that translate knowledge into sustained action at adequate scale. The satellites will keep dying. The debris will keep accumulating. The question is whether the institutions of human civilization can organize a response adequate to a problem of this character before the window for an adequate response closes. That question does not have a comfortable answer yet, but it is the question that matters. The history of satellite failures is long and instructive in ways that go beyond individual case studies. The pattern that emerges from studying the catalogue of on-orbit failures reveals something systematic about the gap between design assumptions and operational reality. Satellites are designed to perform in an environment that no ground test can fully replicate. The combination of high vacuum, extreme temperature cycling, intense radiation, and the microgravity that causes materials to behave differently than on Earth cannot be simultaneously recreated in any laboratory. Engineers use extensive simulation, component-level testing, and subsystem verification to characterize expected performance. But the complete operational environment of a satellite in orbit is assembled only at launch, and sometimes it reveals failure modes that testing missed. The most common unexpected failure mode is what engineers call single-event upsets. These are transient disruptions in digital electronics caused by high-energy cosmic ray particles or solar protons passing through and depositing charge in a semiconductor junction. Most single-event upsets cause temporary errors that the satellite's fault management system can recover from automatically. A smaller fraction cause latch-ups, states in which a component draws excessive current and must be power cycled to recover. An even smaller fraction cause permanent damage to the affected component, requiring that systems be redesigned to route around the failed hardware. Modern satellites are designed to tolerate single-event upsets through redundancy and fault management. But the most severe radiation events, the larger solar proton events associated with major solar flares, can overwhelm fault management systems designed for normal operating conditions. The Carrington event of 1859, if it were to recur, would be by far the largest solar proton event in recorded history. The disruption to satellite electronics from an event of that magnitude would be severe across the entire fleet of operational satellites. The October to November 2003 solar storms, sometimes called the Halloween storms, caused measurable damage to several satellites and disrupted the operations of many more. Several satellites experienced attitude control anomalies. Some recovered, some did not. The storms provided a small preview of what a larger event could produce. Solar particle events create both immediate operational disruptions and long-term damage accumulation. The total radiation dose accumulated by a satellite over its operational life determines, to a significant degree, how long the satellite's electronics remain reliable. Satellites that experience unexpectedly severe radiation environments may have shorter than expected operational lifetimes, not because of any manufacturing defect, but because the radiation environment exceeded the design assumptions. Satellites that fail for this reason fail as dead, propellant-equipped objects with no ability to execute end-of-life disposal. They become debris in whatever orbit they happen to occupy. The space weather problem connects the debris problem to a larger context of Earth's vulnerability to solar activity. A civilization that has placed thousands of satellites in orbit and that depends on those satellites for navigation, communication, weather forecasting, and financial transactions has created a significant vulnerability to space weather events. A major solar storm would simultaneously create large numbers of dead satellites, disrupting services, and it would do so without warning sufficient to allow controlled deorbit of potentially failing satellites. Managing this vulnerability requires both space weather monitoring and satellite design standards that account for the full range of solar activity, including rare but historically documented extreme events. The standards that govern satellite radiation hardening are not currently calibrated to the largest historical events. The satellites currently in orbit were designed for normal solar activity conditions, with margins for somewhat elevated activity. They were not designed for Carrington-level events. In the event of such a storm, the resulting wave of satellite failures could generate a substantial pulse of new debris at multiple orbital altitudes simultaneously. The economics of orbital spectrum and orbital slots provide another dimension to the satellite death problem that is rarely addressed in technical discussions of debris. Geostationary orbit is not just a physical location. It is a regulatory resource managed by the International Telecommunication Union, which coordinates the radio frequencies and orbital positions assigned to geostationary satellites. Each geostationary satellite position is defined by its longitude above the equator, where it appears stationary to ground observers, and by the radio frequencies it is licensed to use. A satellite at a specific longitude using specific frequencies occupies a slot in the geostationary belt. The ITU slot allocation system was developed when geostationary satellites were large, expensive, and relatively few. Each slot represented a major national or commercial investment. The coordination system was designed to prevent interference between satellites in adjacent or overlapping slots, ensuring that the operators of each satellite could use their licensed frequencies without disruption from neighbors. When a geostationary satellite dies, its ITU filing does not automatically expire. The operator of the satellite typically retains the filing rights for the position and frequencies for some period after the satellite ceases operation, which allows the operator to plan and execute a replacement satellite. This retention of filing rights for defunct satellite positions is a significant regulatory complexity that interacts with the debris problem in interesting ways. An operator whose geostationary satellite has died and whose replacement satellite is delayed may retain the filing rights for the dead satellite's position while the dead satellite drifts from the position and the replacement is not yet present. The dead satellite, during its drift, can approach other active satellites in the belt, creating collision risk and potential frequency interference. The dead satellite's transmitters, if they have any residual power, may emit interfering signals on the licensed frequencies. The situation is regulated imperfectly by the existing framework. The ITU's radio regulations include provisions for the suspension and cancellation of filing rights when satellites do not operate for extended periods. But the procedures for invoking these provisions are slow and contested. The filing rights for a dead geostationary satellite may take years to fully transition to a replacement or be released for other operators, during which the regulatory and operational status of the dead satellite's position is in a form of limbo. This creates perverse incentives in some cases. An operator with a dead satellite in a commercially valuable geostationary slot has an incentive to maintain at least a minimal claim of ongoing operations or near-term replacement in order to protect the filing rights to that slot. The filing rights may be worth tens to hundreds of millions of dollars in a competitive commercial market. The incentive to protect those rights may conflict with the incentive to promptly dispose of the dead satellite through a graveyard boost, which requires the satellite to expend propellant moving away from the slot. The regulatory architecture was not designed with this specific conflict in mind. The ITU's role is radio frequency coordination, not orbital debris management. The institutions that manage orbital debris guidelines primarily the IADC and national space agencies, have limited leverage over the filing rights that the ITU administers. The result is a governance gap in which the economic incentives created by the ITU system can work against the debris mitigation goals promoted by the debris management community. Understanding this regulatory dimension is important because it reveals that the debris problem is not purely a technical problem or purely an economic problem. It is also a regulatory problem in which the incentive structures created by existing regulatory frameworks sometimes actively discourage the behavior that good orbital stewardship requires. Solving the debris problem requires addressing all three dimensions simultaneously. There is one final dimension of the satellite death problem that connects the technical and the human in a way that grounds the entire discussion. When we talk about orbital debris, we talk about probabilities and collision rates, and Kessler thresholds and regulatory frameworks. These are the right categories for understanding the problem at a systemic level, but the specific events that drive the debris problem are specific. They have names and dates and circumstances, and examining the specific events reveals something about how systemic problems actually unfold. Iridium-33 was launched in 1997 as part of the Iridium satellite telephony constellation, one of the first commercial satellite phone networks. It was designed to provide voice and data communication to users anywhere on Earth. At the time of its collision with Cosmos 2251 in February 2009, Iridium-33 was a functioning commercial satellite providing services to paying customers. Its collision was not anticipated. The United States Space Surveillance Network tracks all objects in its catalogue and routinely assesses close approach risk. But in 2009, the close approach of Iridium-33 and Cosmos 2251 was not flagged as a high collision risk event before it occurred. Part of the reason for the missed warning was the nature of the tracking data available for Cosmos 2251. The defunct Russian communication satellite was tracked, but the tracking data for inactive satellites from older programs is sometimes less precise than for active commercial satellites. The predicted close approach distance based on available tracking data may have been larger than the actual close approach distance. The combined uncertainty in the positions of both objects was sufficient that a potential collision was not identified as requiring a maneuver in advance. The collision itself occurred over Siberia, at an altitude of approximately 789 kilometers. The combined relative velocity at impact was roughly 11.7 kilometers per second. The collision converted two satellites, with a combined mass of roughly 1,500 kilograms, into thousands of fragments scattered across a wide range of orbits near 789 kilometers. The aftermath required months of intensive catalogue updates as the Space Surveillance Network tracked the debris cloud and assigned catalogue numbers to newly trackable fragments. The cloud expanded along and across the original orbit, and some fragments were perturbed to higher or lower orbits. The International Space Station conducted a debris avoidance maneuver in response to the collision event. Multiple satellites experienced close approaches with Iridium-Kosmos fragments in the months and years following. The Iridium-Kosmos collision was the moment when the abstract concept of orbital debris became an operational reality for satellite operators in a new and concrete way. Before 2009, debris was a recognized hazard, but had not yet caused the catastrophic loss of an active, revenue-generating commercial satellite. After 2009, the insurance industry began pricing orbital debris risk differently. Satellite operators began investing more in conjunction assessment, the monitoring of close approaches and calculation of collision probability as a routine operational function. The collision also revealed a gap in the international coordination of debris avoidance. Iridium operated its satellites from control facilities in the United States. Cosmos 2251, though long defunct, was technically the property of the Russian government. There was no established mechanism for Iridium to receive information about the close approach risk from Russian tracking data, or for any international body to assess the combined collision risk using tracking data from both American and Russian sources. Since 2009, coordination has improved, though it remains incomplete. Commercial space situational awareness services have emerged that aggregate tracking data from multiple sources and provide conjunction analysis to satellite operators on a subscription basis. The growth of these commercial services represents a genuine improvement in the operational awareness of debris risks. But the data underlying these services is still limited by the sensitivity of the ground-based sensors available, and the governance of conjunction warning remains fragmented. The lesson of Iridium-Kosmos is not that the collision could easily have been prevented. The lesson is that the conditions that made the collision possible were systemic: insufficient tracking precision, inadequate coordination mechanisms, and a debris environment populated by dead satellites from programs that left no one responsible for ongoing monitoring or avoidance. The conditions that produced Iridium-Kosmos have not been substantially resolved in the 15 years since. The population of uncontrolled dead satellites in the 700 to 900 kilometer altitude range has grown, not shrunk, since 2009. The next Iridium-Kosmos collision is not a question of if, it is a question of when, and the next one, occurring in a more densely populated debris environment than 2009, will produce a larger debris cloud with more severe downstream consequences. The specific populations of objects in each orbital shell tell different stories about how human activity has shaped the orbital environment. The low Earth orbit population is the most dynamic. Objects enter constantly as new satellites are launched. Objects leave through atmospheric re-entry, both controlled deorbits and natural decay. The net result of these inflows and outflows determines whether the LEO debris population is stable, growing, or shrinking. Current analysis suggests the population is growing because the rate of new object generation from launches and fragmentation events exceeds the rate of natural decay and planned deorbits. The density within LEO varies significantly by altitude. The 400-kilometer altitude where the International Space Station operates is relatively uncrowded, partly because the atmospheric drag at that altitude decays any object within a year or two without active orbit maintenance, and partly because the ISS's presence motivates careful collision avoidance. The 550 to 600 kilometer altitude where Starlink satellites operate is the most densely populated region of LEO, with thousands of active satellites in a relatively narrow altitude band. The 800 to 1000 kilometer altitude, as discussed, is the most debris-dense region due to the accumulation of historical satellites and fragmentation events combined with the weaker atmospheric drag. The MEO population is smaller in total number of objects but contains a significant concentration of risk. The GPS and Galileo satellite constellations orbit in MEO, and their altitude range coincides with the inner edge of the Van Allen radiation belt, the outer radiation belt, and the region between the belts. Objects in MEO experience intense radiation environments that degrade electronics faster than in LEO or GEO. The radiation environment also makes active debris removal from MEO more challenging, because removal spacecraft would themselves be exposed to the intense radiation while conducting operations. The geostationary belt contains roughly 550 active satellites at any given time, and more than 750 non-functional objects, for a total tracked object population of well over 1,300 in and near the geostationary ring. These objects are distributed around the equatorial ring, clustering in regions of high commercial value, where coveted orbital slots bring high prices in the regulatory market. The clustering means that in some portions of the ring, dead satellites are in close proximity to active ones. The distribution of objects in the geostationary belt is not uniform. Orbital slots over certain geographic regions, particularly over the Americas and over the equatorial Pacific, are more valuable than others because they provide coverage of densely populated and commercially active areas. These regions attract more satellites, and therefore more dead satellites, as operators have historically placed the most satellites in the most valuable positions. The specific category of rocket bodies deserves separate attention. A rocket body is the upper stage of a launch vehicle, the component that provides the final thrust to place a satellite in its target orbit. After releasing the satellite, the rocket body is left in space, typically in an orbit that is similar to the satellite's target orbit. Rocket bodies are generally much larger than the satellites they carry, and have no mission value once the satellite is separated. Many have been left in orbit without any end-of-life disposal. Rocket body explosions have historically been a major source of debris generation. The residual propellant remaining in a spent rocket stage after orbit insertion is sufficient to cause a catastrophic explosion if the propellant, oxidizer, and pressurant systems are not properly vented and passivated. Before passivation practices were established, spent rocket bodies exploded with some regularity, each event generating hundreds to thousands of fragments. The practice of passivating rocket bodies, releasing all stored energy through controlled venting, has significantly reduced but not eliminated rocket body explosions. Older rocket bodies in orbit, from eras when passivation was not practiced, still carry residual stored energy and continue to pose explosion risks. Several rocket bodies from 1970s and 1980s launches are believed to have exploded in orbit within the last decade, generating new tracked debris clouds without any warning to the satellite operators sharing their orbital altitude. The international effort to track and characterize all of these populations, to understand their growth rates and their collision probabilities, and their expected evolution, is ongoing and important. Organizations including NASA's Orbital Debris Program Office, ESA's Space Debris Office, and equivalent organizations in Japan, Russia, and China maintain models of the debris environment and produce regular assessments of the population trends. These assessments drive the policy discussions and the urgency assessments that shape debris mitigation standards. The assessments converge on a consistent conclusion. The trend in the debris population is unfavorable. The most critical orbital shells are approaching or have already passed stability thresholds, and the gap between the mitigation measures currently in place and the measures required to reverse the trend is very large. There is one failure mode of satellites that receives less attention than it deserves: the failure that happens after the end of an operator's business. The commercial space industry has grown dramatically in the last decade. Where once the dominant satellite operators were national space agencies and large telecommunications companies with stable, long-term business models, the industry now includes hundreds of smaller commercial entities, including startups with uncertain financial futures and business models that depend on market conditions that can change rapidly. When a satellite operator goes bankrupt or otherwise ceases operations, the satellites the operator launched remain in orbit. The satellite's country of registration retains legal responsibility under the Outer Space Treaty. But the country's practical ability to conduct end-of-life operations on behalf of a failed commercial entity is limited. The country must either find another operator to assume responsibility, use government resources to conduct end-of-a-life operations on the failed operator's satellites, or acknowledge that the satellites will become uncontrolled debris. The specific mechanics of satellite operations require authorization from the country of registration to operate. A satellite's onboard software typically requires periodic command uploads from the ground to maintain operations. Without those command uploads, the satellite's software may cycle through fault recovery modes, exhaust stored propellant in unplanned maneuvers, and eventually transition to an uncontrolled state. The case of LeoSat, a startup satellite broadband company that raised hundreds of millions of dollars before failing to close additional funding in 2019, illustrates the issue. LeoSat folded before any of its planned satellites were launched, so no debris was created by this specific failure. But the scenario of a company failing after launching satellites is not hypothetical. Several small satellite operators have launched CubeSat constellations and subsequently failed or significantly reduced operations, leaving satellites in orbit without active management. The regulatory response to the risk of operator failure has been imperfect. Some regulatory bodies now require satellite operators to post bonds or demonstrate financial assurance sufficient to cover end-of-life disposal costs. These requirements provide some protection against operator failure during the operational phase, but they are not universally applied, and their adequacy depends on assumptions about disposal costs that may be exceeded if the operator's satellites are in less accessible orbits or have experienced anomalies that make standard disposal more difficult. The demographic diversity of the commercial satellite industry also creates a challenge for debris mitigation enforcement. A large, established satellite operator with ongoing business in a jurisdiction has significant incentives to maintain good standing with that jurisdiction's regulatory body, which creates leverage for enforcing debris mitigation requirements. A small startup operator with limited assets and uncertain longevity may have much weaker ties to any jurisdiction's enforcement mechanisms. The enforcement challenge grows as the industry becomes more diverse and distributed. One response to the challenge of small operator accountability has been the development of hosted payload arrangements, in which small operators' hardware rides as a secondary payload on a larger satellite operated by a more established entity. The host operator bears responsibility for the overall satellite and its end-of-life disposal, providing a backstop for the smaller operator's debris responsibilities. But hosted payloads cannot accommodate all small operator missions, and the trend toward dedicated small satellite constellations limits the applicability of hosted payload approaches. The failure modes of the commercial satellite industry, as distinct from the failure modes of individual satellites, represent a growing source of debris risk that was not a major consideration when the current regulatory frameworks were developed. Addressing this risk requires both stricter regulatory requirements for financial assurance and clearer legal frameworks for the transfer of responsibility when operators fail. These are governance challenges as much as technical ones. The mathematical framework that underlies the Kessler syndrome analysis deserves some unpacking, because it reveals why the problem is harder to stop once started than it is to prevent from starting. The key quantity in the Kessler analysis is the collision rate between objects in a given orbital shell. The collision rate depends on the number of objects in the shell, their physical sizes, and their relative velocities. As the number of objects increases, the collision rate increases as the square of the number. Doubling the number of objects roughly quadruples the collision rate. This superlinear relationship is what makes the cascade dynamics possible. At low debris densities, the collision rate is low enough that the rate of new debris generation from collisions is less than the rate of debris removal through natural decay. Under these conditions, the debris population in the shell is stable or declining, even without any active management. This is the stable regime. As debris density increases toward the threshold, the collision rate increases faster than linear. At some critical density, the collision rate generates new debris at exactly the rate that natural decay removes debris. This is the threshold. Below the threshold, the system is self-correcting. Above the threshold, the system is self-reinforcing. Above the threshold, even a complete cessation of all new launches would not stop the debris accumulation. The existing objects would generate new collisions. The new collisions would generate new fragments. The new fragments would generate more collisions. The rate of debris generation would accelerate until the objects were too small to generate significant new debris, at which point the cascade would slow, but the orbital shell would be densely populated with particles too small to track. The specific time constant for the cascade is measured in decades to centuries, depending on the altitude. At 800 to 1,000 kilometers, the cascade, once started, would proceed over a timescale of decades to centuries before stabilizing at a new, much higher debris density. The new equilibrium would not be an equilibrium in any operationally useful sense. It would be a debris field dense enough to make sustained operations in the altitude range essentially impossible. The threshold density is not a sharp line. Different researchers have placed it at somewhat different values depending on their assumptions about the size distribution of existing debris, the collision cross-sections of debris objects, and the solar activity that drives atmospheric decay rates. But the range of estimates converges on a conclusion that is broadly consistent. The most critical LEO altitude ranges are within a factor of 2 to 3 of the Kessler threshold, and some may have already crossed it. The asymmetry between prevention and remediation is the most important practical implication of the Kessler analysis. Preventing the cascade requires maintaining debris density below the threshold, which means managing the rate of new debris generation against the rate of natural decay. This is achievable through a combination of improved debris mitigation practices, reduced fragmentation events, and improved tracking of existing debris. Arresting the cascade once it has started requires active debris removal, but the economics and logistics of active debris removal at the scale required to reduce debris density below the threshold in a specific altitude range are orders of magnitude more challenging than the economics of preventing the density from reaching the threshold in the first place. This asymmetry argues strongly for aggressive prevention now, before the cascade dynamics become irreversible in specific altitude ranges. The cost of prevention, measured in improved satellite design, stricter compliance with deorbit requirements, and modest investment in debris tracking and coordination, is far lower than the cost of remediation once a cascade is underway. The prevention window is still open. But it is a window with a closing date, and the date is uncertain but not distant. The specific year at which any particular altitude range crosses the irreversible threshold is not known. It depends on the specific trajectory of future launches, the specific failure rates of large constellation satellites, the specific behavior of existing large debris objects, and the specific solar activity that drives atmospheric decay. Models can identify ranges of probable threshold crossing dates, but not precise years. What the models agree on is the direction. The trend is toward higher debris densities in the critical altitude ranges. The trend has been consistent over the last decade. The specific events that would reverse the trend, aggressive active debris removal combined with much stricter compliance with deorbit standards, are not yet occurring at the scale required. The Space Situational Awareness System, the network of sensors and software that tracks the objects in orbit and warns satellite operators of potential collisions, is itself a critical piece of infrastructure that is less well understood than the satellites it monitors. The primary tracking system is the US Space Surveillance Network, maintained by the US Space Force. The network uses a combination of phased array radars, mechanical track radars, and optical telescopes distributed at sites around the world. The radars are most effective for tracking objects in low Earth orbit, where the radar return from small objects is sufficient for detection. The optical telescopes supplement the radars for tracking objects at higher altitudes, where radar sensitivity is insufficient, but telescope observations of sunlit objects are feasible. The catalogue maintained by the 18th Space Control Squadron contains the orbital elements, position uncertainties, and physical size estimates for all tracked objects. These data are used to generate conjunction data messages, automated warnings sent to satellite operators when a tracked object has a significant probability of coming within a dangerous distance of the operator's satellite. The threshold for issuing a conjunction data message is a probability of collision greater than 1 in 10,000, though operators may request notifications at lower probability thresholds. The Space Force shares the catalogue data and conjunction warnings with commercial operators and with foreign governments through various data sharing agreements. The sharing is not universal. Some data is classified, particularly for objects associated with military surveillance programs. The limited sharing of classified tracking data is a genuine operational challenge for the satellite operator community, because the most precise tracking data for some objects may be unavailable to operators who need it to conduct accurate collision avoidance assessments. Commercial companies have emerged to supplement the government space surveillance system. Companies including Leo Labs, Exo Analytics Solutions, and others operate private radar and optical sensor networks that provide tracking data and conjunction assessment services to commercial satellite operators on a subscription basis. These commercial services can in some cases provide more detailed tracking data for objects in their coverage areas than the government catalogue provides, and they can provide services tailored to the specific needs of their subscribers. The proliferation of commercial space situational awareness services has improved the operational awareness of satellite operators significantly compared to a decade ago, but the underlying tracking data is still fundamentally limited by the physical performance of available sensors. Better sensors could track smaller objects and provide more accurate orbital parameters for known objects, but better sensors require investment and take years to develop, qualify, and deploy. Tracking small debris is particularly challenging. Objects smaller than 10 centimeters in LEO are fundamentally below the detection threshold of existing ground-based radar systems. Detecting 1 centimeter debris in LEO would require radars with apertures measured in hundreds of meters operating at high frequencies far beyond what has been built. The theoretical possibility of tracking smaller objects exists, but has not been translated into operational systems. One approach to characterizing the sub-centimeter debris population, which cannot be tracked individually, is statistical characterization through laboratory hypervelocity impact experiments. Firing simulated debris particles at satellite surface materials at orbital velocities produces damage patterns that can be compared to the damage observed on returned spacecraft surfaces. The Space Shuttle returned numerous surfaces over its operational life, and the impact craters on those surfaces provided direct evidence of the flux of sub-centimeter debris at shuttle operating altitudes. Similar experiments with sample return missions and cargo deliveries to and from the ISS provide ongoing characterization. The statistical picture from these impact flux measurements is consistent with the models. There are many more small particles in orbit than large ones, and the sub-centimeter population poses a significant accumulated risk to operational satellites even if no individual impact is catastrophic. A 1 millimeter particle striking a solar panel at orbital velocity can damage individual solar cells. A 1 centimeter particle can penetrate a satellite structure. A 10 centimeter particle can destroy a satellite. The invisible layer of the debris problem, the sub-centimeter population that no tracking system can see, is in some ways the most operationally immediate challenge for satellite operators. It is the debris that will eventually end the useful life of any satellite through accumulated surface damage and the occasional penetrating impact. It is the debris that cannot be avoided because it cannot be detected in time. And it is the debris that would grow most rapidly in a Kessler cascade, as fragment-on-fragment collisions produce ever smaller particles that fill the orbital shells with an invisible, penetrating hazard that no satellite surface can fully resist. The future of the orbital environment is not fixed. It is being determined now by the decisions of satellite operators, by the regulations that governments adopt, by the international agreements that are negotiated or not negotiated, and by the pace of technology development for debris tracking and removal. Several scenarios are possible. In the best case, the regulatory tightening that began with the US FCC's 5-year deorbit rule spreads internationally. Compliance rates improve substantially. Active debris removal technology matures sufficiently to allow selective removal of the largest and most hazardous objects in critical orbital shells, and the debris environment in the most critical orbital shells stabilizes rather than cascading. This scenario requires coordinated international action and sustained technical and financial investment that has not yet been demonstrated at the required scale, but it is not physically impossible. In the intermediate case, some regulatory improvement and some technology development occurs, but not enough to fully stabilize the most critical orbital shells. The debris density in the 800 to 1,000 kilometer altitude range continues to grow, though more slowly than without any intervention. Satellite operations in this range become progressively more expensive and risky. Some applications move to different altitudes. The range is not lost, but it is degraded, and recovering it from a slow cascade would require a sustained active removal effort that may take decades. In the worst case, the cascade dynamics in the most critical orbital shells become self-sustaining faster than intervention can prevent. The 800 to 1,000 kilometer range becomes effectively unusable for new commercial satellite deployment within decades. Some scientific missions that operate in this range are lost prematurely. The debris cloud from the cascade gradually populates the surrounding altitude ranges, pushing the problem to new altitudes. The cascading represents a permanent and irreversible narrowing of the orbital environment available to human civilization. The decision point between these scenarios is not a single moment. It is a continuous process of decisions by hundreds of actors across dozens of countries and companies, accumulating into a trajectory that will determine which scenario unfolds. The conversations happening now in regulatory bodies and space agencies and commercial companies and international forums are the conversations that will determine the trajectory. They are happening against the backdrop of an orbital environment that is under measurable and increasing stress. They are happening with the technical knowledge needed to understand the stakes. They are happening with the engineering capability to build the systems needed to address the problem. What they are not happening with is the speed and scale and international coordination that the problem requires. Vanguard 1 is still up there, as it has been for more than 60 years. Whatever happens to the orbital environment in the decades ahead, Vanguard 1 will watch it from its perch between 3,760 and 4,900 kilometers altitude. Still silent, still patient, still completing one orbit every 133 minutes with the precision that orbital mechanics demands. In 2020, if the orbital environment has been managed well, there will be tens of thousands of functional satellites providing services to a human civilization that has spread across the Earth and perhaps beyond. Vanguard 1 will still be there, the oldest surviving artifact of the space age, an inadvertent monument to the moment when humanity first reached beyond the atmosphere. In 2200, if the orbital environment has not been managed well, the view from Vanguard 1's altitude may be very different. The shells below it may be thick with fragments, the remnant of cascades that were allowed to develop. The satellites that might have operated there may be absent, their altitude ranges effectively abandoned. The choice between those futures is still available. The window is still open, but Vanguard 1 is not waiting. There is a specific image that crystallizes the problem more vividly than any statistic. On February 10th, 2009, at 1656 UTC, a collision occurred 789 kilometers above the Taimyr Peninsula in Siberia. Two satellites, one active American commercial satellite and one defunct Russian military satellite, converged from their respective orbits at a combined relative velocity of roughly 11.7 kilometers per second. Neither saw the other coming. There was no avoidance maneuver. There was no warning sufficient to act on. There was a moment of contact so brief that no human perception could have registered it, and then two satellites became thousands of fragments. The debris cloud expanded along the orbital path. The fragments followed their own individual trajectories, some slightly higher than the original orbit, some slightly lower, spreading out along the altitude band. Within hours, the debris cloud had thinned enough to be undetectable as a concentration, but are distributed enough that every satellite operating in the vicinity of 789 kilometers altitude was sharing its orbital environment with fragments from two machines that no longer existed as machines. In the years since 2009, the fragments from that collision have spread further. Some have decayed to lower altitudes. Some are still in orbits close to where the collision occurred. Each one is a potential source of further fragmentation if it collides with another object. Each one is too small to be tracked reliably. Each one is moving at approximately 8 kilometers per second. The collision was not an act of malice or negligence in the immediate sense. It was the consequence of 62 years of putting objects in orbit without adequate planning for what happens when they stop working. It was the product of a decision made by every space agency and every satellite operator from 1957 onward to treat the orbital environment as an infinite sink, a place where dead machines could simply be left without consequence. The orbital environment is not an infinite sink. That conclusion has been available in the physics since Kessler published his analysis in 1978. It has been available in the operational data since the tracking catalogue began filling with objects that do not deorbit. It has been available in the insurance actuarial tables since operators began calculating collision premiums. What has been missing is not the knowledge. It is the collective will to act on the knowledge at the scale the problem requires. That gap between understanding and acting is the core of the challenge that the orbital environment now presents. The satellites that are dying in orbit today will be the debris cloud of tomorrow. The decisions made now about deorbit requirements, about active removal programs, about international governance will determine whether that debris cloud is managed or whether it becomes self-sustaining. The window for the right decisions is the same window that has been open since 1978, getting narrower every year. Vanguard 1 completes another orbit. The catalogue grows by a few more objects. Somewhere in a control room, an operator schedules a collision avoidance maneuver for a satellite that was built to do science, and is now doing mostly that, avoiding other things. The sky above Earth is not empty. It has not been empty for a long time, and what lives up there, in the dark between the stars and the atmosphere, matters more than most of the people who depend on it know. Strap in, keep looking outward, and stay with the crew. If you want more mission briefings like this, subscribe for the next journey.